busy?
Hmm?
Are you busy?
Yes,
Sorry.
you're good. Okay. Now the recording has started. Now we can send it out.
It's like, once you finish part A, you just turn it in, the rest of the time you just do. Thank you.
Exactly. So to recap, there will not be op amps on the final.
Yeah, we've been going from one room to another.
I know. I'm so sorry. Today's been a mess. Today's been so crazy.
Final semester.
Is that a mic I hear?
Yes, it is. It is. It is Mike. I'm gonna share my screen up there. I think it'll be better when the lights are off, but we'll keep it on for now. You're good. We'll keep them on for now and we'll see if it does better. So op amps, not on the final problem solving part. I'm not gonna promise that they won't be on the conceptual part, but if it would be basically like, what's gain? That's a really fair question after I said that. Basically gain is just the proportion of how much voltage is coming in versus coming out. It's not too complicated, but then op amp's not there. There's 5 problems. There's gonna be 5 problems for the problem solving part. As for timing, you will start with part A. You will have all of your information, all of your notes in your bag. You won't be able to take them out. Can you crack that door really quick? Thank you. You will take as much time as you want for part A. Then you will come turn it into us. We will give you part B, and then you can take out your notes. You can take out anything you want. Thank you. And then you have as much time for part B until the 2.5 hours is up. This test will be a lot less of a struggle. Time-wise, you have essentially an extra hour to do it. Don't take a lot of time on part A. If you don't know a question, put something down and move on. They are pretty, if you don't know them, you don't know them. No. No. So part A is 20 questions and it is worth 20 points of your exam. So each question is 1 point, and then the other part is going to be 80% of the exam.
Since the second part of the exam is worth 80%, I'm guessing like the highest grade that can replace our first midterm is 80.
That is an excellent question as well. So
Okay.
what we're doing is the percentage out of 80. So on the final exam, the second part is worth 80% of the final. What we're letting replace the midterm is your percent out of 80. Yeah.
Gosh.
Yes. So if you get 40 out of 80 points, it replaces with a 50 instead of a 40. Because it's 50% of 80. That makes sense.
Yeah.
Sweet. Yes. I'm putting out an announcement.
Would you say the best source for part B would be like problem sets and the exam or the past two midterms? Are there other problems then we can get from just for more?
That is the biggest question that I get. And I have a terrible answer of there's no extra problems because Russell makes his problem so specific and he changes them up a little bit for the final, but he wants to kind of keep his bank. Some professors do the same thing on other exams, like they don't give out their exam questions. Every single one of your homework questions is a past exam question. Every single one of them. He's given on an exam at some point in time.
And you don't have access to like.
Well, I have access to them, but Russell's asked me not to do that.
I understand.
No, you're good. Then, yeah, pretty much that.
And also in the other two reviews, the questions are also different than the problem sets too, so we can also go back to the.
Yes. So go back, watch my previous reviews. There's reviews also on this Teams channel. Some of which I've done, some of which other people have done. Oops. Yes, those are good resources. And I think today, one of the things we're gonna do is go over that switch problem on your midterm, because he hasn't put out the solutions yet. And I think that was a big, hard question. So that's one of the ones that we're gonna go over today for the switch problem. I can also go ahead and say, the 5 questions that are gonna be on the exam, I have them written down. I have the concepts written down now. It's gonna be an E shift or an I shift problem. Which we're gonna go over today. It's gonna be a current divider, a source transformation one, name or Thevenins. Oh, and then second order, there actually isn't gonna be a switch problem on there? Okay,
I'm just kidding.
okay. As what Russell says that, I normally believe Russell. Russell has changed his mind last minute before. And I have gotten in a bit of trouble before. Because I was like, it's gonna be Thevenins, and then he puts Nortons on there. And it was terrible too. Because he changed it the night before. He changed the test, like he gave me the exam, and then the night before he changed the problem.
That's crazy.
I love Russell. I really do. I was a little annoyed that day.
An interesting man.
He is an interesting man. But what we'll do is we'll go over those concepts, and if at the end you want to watch me go through that midterm switch problem, we can do that. Then let's see, what other questions? So those are what's going to be on the exam. What else do we have? Yes, I will do that today. Yeah. Yeah.
Is that out of 10? Is like the whole score.
So they're out of 100%, but then it counts for 10% of your total grade.
Yes, it's the 3.
Yes, yes. Problem set 4 will be graded. It just might not be graded until the end of the semester. Because we did midterm 2 so late. That it was a bit rough on the turnaround for trying to get y'all your exam 2 back for the final. Because I want y'all to have that, and I know that that's going to be more important than anything else. So, what else we got? Questions?
The name and main stuff, it's like, it's not just resistors, it's gonna be like inductors, capacitors. like everything.
He's saying name or thevenins, which to me takes that as just passive with dependent sources. He said second order, he didn't say steady state. Which steady state is the name and MAME with inductors and capacitors and all of that. So go ahead.
It just seems weird that there's like none of these questions are about that.
I agree. However, I'm gonna say, yeah. Yay. Right?
So the switch is not gonna be on it,
Maybe.
It does appear that way.
but still go over it.
I would say go over it at the end. Focus on what we go over today for sure, but no. And then switch questions will be on the conceptual part. So know some of those, that's a good one. Some of the verbiage, right? For those things, think about what transient is. And I have to be very careful on telling y'all what to study on part A because they don't change too much year to year. I have to be very vague. I can't explicitly. Touche is what I say to that. I would say go over concepts. So don't start from day one. Say, let's see. We've gone over these big concepts in this class. Let's think about, like, at its core, verbiage. Say KVL and KCL. What is KVL and KCL? From a very, like, conceptual part. There's not going to be any math on the first part. There's not going to be any, like, you won't need a calculator, anything like that. Just go over main concepts and then be like, okay, can I explain to someone else from a very conceptual part, like KVL? Textbook definition, what is KVL? A little more than that, not a hypothetical question. This is me actually asking.
Oh, okay. The sum of voltage drops around a loop should sum to 0.
Exactly. Sum of voltage drops around a loop should be equal to 0. That is what it means. Know that level of stuff.
So not too terribly basic, but like, because you could say that KVL and KCL are essentially energy conservation. It's like not more specific than that.
Yes, but also know that. That is also a really good thing to know what you just said. He said it's energy conservation. Remember that. Remember that.
Guess some diodes are gonna be on
No.
there.
No. Diodes? We don't go over diodes and circuits. That's electronics. It's passive and active. That's electronics. The highest level would probably be second order. And if you ask, okay, second order, what type of second order things would be?
Damping. Critically
Mhm.
damped.
Critically damped. What does oscillatory mean? Is that underdamped?
That's what it could be either, really.
It's
If it's overdamped, then you have overshoot. If it's underdamped, then you're undershoot.
you're just gonna need to know, you're not gonna need to know overshoot and undershoot. Just undamped, overdamped, critically damped.
Did you say the averages for the final is like drastically higher than the midterms usually?
I hope it is this semester. The averages this semester have been lower than I thought they were going to be. They've been lower this semester than they have other semesters. And I don't exactly know why. I really don't. So I'm hoping that y'all do better on the final. It doesn't seem like it's going to be too terribly difficult from what Russell has shown me. So I think y'all are going to be okay. But any more questions before we get into problem solving?
The materials you said, 2D, is that it?
Mm-hmm. Yes, so helpful materials. Z1 for second order. Said it a million times, and I know that. If you want to look at source dominance or transformations, chapter 2 is a great resource. If that earlier stuff wasn't fully clicking.
About shifting.
Is that in chapter 2? That actually might be in chapter 2.
Sounds right.
I think it is. I was just gonna pull it up really quick. And I think he may have posted that. Oh, did he change it to resistor doc too? No, that's completely different. Never mind. Some of them, if you want, there's some extra examples of Mayman name in the materials that he posted. Those are good. If you want some extra examples. And then in some of his materials, there's a couple extra examples in there too. So those are good to look at. Yeah, that's what I got on that. Okay. If y'all don't got anything else, we'll go on to problem solving. Yeah? Okay, cool. We'll go ahead and start from where y'all might not fully remember because it was forever ago. And we'll start with shifting. I'm sure that's been a minute for y'all. I'm looking at chapter 2 really quick because I think it actually might be in there. Yes, so if you want also some more documentation on shifting, look into chapter 2. And then we'll go ahead and get started on that. So a couple of these we're just gonna do straight from your homework, but we're gonna go over it and we're gonna remember exactly how to do it. So let's do share screen. Okay. Do we wanna do lights out? Could one of y'all get the lights out while I try to make this full screen? Is there? Is that good enough? I don't know how I can make this also go bigger screen. So is that okay? Ish?
That's perfect.
Okay. So 1.167, this is right from your homework. So number one, and I say it every time, I am guilty of it. Read the question. I saw a lot of people on midterm 2 not write out the equation for the switch problem. It was
Guilty.
part B. It just said to make sure you write out that full equation where it's like I infinity or V infinity plus that whole thing. And that was an extra like 3 or 6 points. Make sure you read the whole question. Make sure you know all of that. So how's that look? Okay, cool. Cool. So let's read the question. Using the component value shown as below, you are asked to do the following. Reduce the network by shifting J1 around resistors R2 and R3 and shifting E2 through node 2. Then use source transformations and combinations to produce an equivalent containing only resistors and voltage sources. And then use the reduced network to calculate the voltage V1 across the current source. So I'm going to zoom in if everybody has got that down. So first step, and he actually tells you the first step, which is really nice on this one specifically. So we're going to look at this and we're going to try to I shift it. Now, do we remember how I shift works? Nope. And that is expected. And that's why we're here. So the way that I shift is going to work is we see that there is this node and there is this node, and there's current flowing from this node to this node. What we can do with I shift is pretty much a conservation of current. Since current's flowing from this node to this node, what we can do is we can split it up. We can split it up so that current is still flowing from that node to that node, but they're going to be an intermediate step. Because let's say it tells you to shift it around resistors 2 and 3. Right? 2 and 3. We can say that if we have current flowing here, so if we have that same current flowing there, but then we have that exact same current flowing back over here, is that any different than flowing up there?
No.
Mm-mm. Does it seem like it would be?
I guess so.
Why? There's that weird second node. But if we look at it, we have 3.75 flowing in, but we're accounting for that by having 3.75 flowing directly back out of it. So it is essentially a net zero. So none of that is going to affect whatever current is flowing through here. A little weird, a little funky, but it maintains KCL. It keeps everything the same. But it's super helpful because now if we do that, and I'll go ahead and draw it out. Is that thick enough? Do y'all want me the pen to be any thicker for people here? Okay, cool. So let's go ahead and do that. So I'll go ahead and draw this, and then I'll draw this. And which way is that going to be pointing? Are they both going to be pointing the same direction?
Yes.
Remember, we have to have it flow from VN3 to VN1. So they both need to be pointing that direction. So now we see, do I have a, no. See, we have this and this. Oh, that is large. Can we do anything with these? We can now transform these and make it a lot simpler to solve. And that's the whole point of shifting. It is, instead of it going over 2 resistors, it's making sure that they are only going over 1 resistor each. So let's do that. And let's come over here and we'll redraw the circuit. So now I'll keep everything the same at the bottom. But do we want to go ahead and transform it? Are we good to go ahead and transform it? Okay.
Yeah.
So transformed, it's in parallel and it goes to in series. So we're going to have a voltage source here. And then we're going to have another voltage source pointing that same direction, and then a resistor. 200, 9, we have 600. And then what are those values? So we had 3.75 milliamps and 2.4 K. So what's that voltage going to be? If someone could get their calculator, that would be very much appreciated. Okay, 4.5. Does the resistor change or stay the same?
Stays
Yes,
the same.
sir. And then R3? Or for R3, the voltage. 9 volts. Sweet. So there is the first step. We did the first step. Now let's look at second pair of instructions. We need to shift E3, E2 around node 2, through node 2. Words are hard. So E shift. We went over I shift. How does E shift work? A little funkier. Yeah.
Why is there?
Was it not 600? It was 360. Yeah, that's because I wrote it wrong. Good catch. Thank you, sir. They should have all stayed the same. Yeah. No, so those these two are in series here. These are in series. So the order of those two does not, why, what? That's stupid. This is why I like dot cams more than computers, but it's been a day. So, yes. Mm-hmm.
I just decided to have registered vote.
Yeah. The reason I did that personally was so that the voltage sources would both be closer to the nodes. But that's pure preference and there is no reason for that. You could have done the other way around. Or you could have them both different ways as long as this side is plus and this side is minus. Same over here. Because those current sources were facing left. So the voltage sources also need to be facing that way. But skipping ahead. So E shift, a little funkier. So I'll start very similar to KCL. I shift works with KCL. E shift works with KVL. What we need to maintain for E shift is the voltages around both loops. So we have this loop and this loop, right? So we see that for this loop, loop 1, loop 2, loop 1, we have basically -9 volts because it's flowing in that positive terminal and out that negative terminal. And then on the loop 2, we see that it is plus 9 volts. So it's flowing in the negative terminal and out the positive terminal. So we don't like that there is a voltage source in the middle because it makes things inconvenient for us. So what we can do is we can, I like saying we like push it up, kind of like punch it. And then what happens is it goes through that node and then it splits out. And what that does is, so it's going to go, I'm going to just butcher this drawing. It's going to go up and then out, up and then out that way. So what this does is it makes it so that there are now 2 voltage sources where it maintains KVL. It splits it into 2, but it's the exact same. I'm going to go ahead and draw it and then we can look at it if it's confusing. So this stays the same, 360. We still have that 1.2K. We have this 4.5 volts. And then we have this way, 9 volts. And then now, since we pushed it up, we just have a wire. We pushed up this basically part of the wire. I'm just going to use a million different colors. And since we pushed it up through that wire, we just have a wire there now. So now on the other side, our 9 volts now is pointing the other direction. And then we have 9 volts here. And then we have a resistor, and then we have a resistor down here. Oops, don't do that. Don't do that. So now we have 2 loops, and this is going to make it a lot easier to solve. How can we make this easier to solve? First, let's combine voltage sources, right? Okay. So we can combine these 2, right? What does that make? 13.5. So I'm just going to draw these resistors again. My very, very ugly resistors. Oh, what about this? They cancel out. So they are going opposite directions. Now we just have a wire.
think the rightmost resistor is 200.
Yes. So now what can we do? Mm-hmm.
Wait, since there's just a wire now in between them,
Mm-hmm.
can we just get rid of the right side?
Yes.
Why do we keep that wire up there?
So, we keep the wire there because we shifted that voltage source up, right? Because we shifted it up, we keep that, we shift up through the wire. So we don't get rid of that wire. We're shifting it through the wire, but we're essentially using the wire to push it up. And this is all very visual. But a more mathematical way to say it is we still have those two loops, right? We need to maintain those two loops. What do you mean?
You keep the wire so that it's parallel.
Mhm.
It goes down exactly short circuit.
It is a short circuit. How do I, hang on. I want to do something really quick. I didn't change how I shared everything. And I didn't do just one window, which is what I meant to do. And I want to make sure we didn't. I'm pretty sure this is right, but I always check things to make sure I'm doing things right because I mess up. Okay, yeah. So now what is the next step? And I am about to go back, share my screen. Need to go back to Teams, go back here, share window. That is what I wanted to do. Okay. Come back to the question. We want to find the difference between VN3 and VN1. So we already said that this is a short circuit. Does that mean that any current is going to be flowing this way? It is not. Because if there is no resistance here, then why would it go through something that's infinitely more resistance? Exactly. So what is the voltage at VN3? I think that was VN3. VN3 is equal to 0. So now all we need to do is find what the voltage is at VN1. How do we do that?
Find the voltage drop across the 1.2K and subtract that from the source.
Exactly. Because we also, and I didn't draw this, but it's also important, we have ground here, which means that the voltage here is going to be 0. So we can find what's the current in that loop. That's how I would do it. There's 2 ways to do this. There's finding the current in the loop or doing a voltage divider. I typically go current in the loop. Do y'all like that, or do y'all like voltage divider? Sweet. That's the way I like. So we have our lovely V is equal to IR. So what's our current going to be? That, I believe it. .58K, which is equal to, what'd you say? Well, it's 3. Oh, yes.
8.654.
0.65.
Yeah.
Okay. So now from here, there's, nope, it's the other way. Right? It's this direction. Because we have our plus minus, current is going to flow from negative to positive with our source. So 8.65 milliamps, we can do what Wes said, find what is the voltage drop over this resistance. Oh, why'd you do that? Let me know when you get the voltages. Yeah.
Just to end. Left side, or if you could, yeah. Twice down the left side and down the.
Okay, so let's look at our loops, right? So on this loop, loop 1, we see that when we are going in the clockwise direction, we see a plus and then a minus, right? We need to conserve that, and we need to, whenever we go in the clockwise direction, we need a plus and a minus. So we need that same thing over in 2. Whenever we go in the clockwise direction, we see a negative and then a plus. So we need that over here, so that when we go in our direction that I chose, we see first a negative and then a plus. And then we can also see that kind of whenever we push it up. So we have our source, And our node, whenever we push it up, it's going to the right on that side, right? And then when we push it up over here, it's going to the left. We see that our plus is on the top, which that means that it's going to be on the far side. So on this one here, we see that it's flowing up and this way, which really means that, and maybe this is weird, it's a plus and the plus go in here, plus, 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 plus. So then it's plus, minus, plus, minus. We go over here, same thing. So that means it's going to be plus, minus, stop. Plus, minus, plus, minus. Does that kind of make sense? Okay, sweet. It's confusing. It's the weirder of the two, I think. So voltages, what do we got? Okay, so we can do 13.5 minus 10.385, which gives, so we can also see that it's just equal to what the voltage drop over VR1 is. It's the exact same. So this is our voltage, and we finished the problem. Right? Everybody pretty good with that? Okay, took a little extra time because we haven't done this on an exam. So now we're gonna move on to current division. Okay, we can do current division. Did I get a current division problem? Of course I didn't. Did I get a did I grab a current division problem? Here, we're gonna do source transformation first because I didn't grab a current division problem yet. And what I might, depending on how much time we have, because I always take way too long on these. We might, I did a current division problem on my first review, and it's basically the problem that I would have done. And so I might say, go watch that one if it didn't cut it off. Crap. Did it cut that one off? The current division problem
From the first exam?
for the review. I know. I'm sorry. Okay, we're gonna do a problem that I also didn't pick. Okay, but I have that one ready. I was so late today. I woke up late, got here late, did all the things. Sorry. Sweet. Okay. Let's do this. You all may have had this one on your homework, but we're just going to do it again together. So network consists of resistors, batteries, and current sources. Use operations of source transformation, source combination, and resistor combination to reduce the network, which means can't do KVL, KCL, you got to do the source transformations. So we remember that the two that you can go between are current source in parallel with the resistor. Wow, that is the worst resistor I have ever drawn in my life. And resistor in series with the battery. And if we remember, source domination only works when there are not resistors in series or parallel. If there is a resistor in series with a voltage source, it cannot dominate. And if there is a current source in, well, it's mainly just voltage source. It cannot dominate. You can't just cancel everything out. So let's start this one. So what can we immediately do? What do we immediately see? Yep. So we can do that. However, we can also look at this. And I've said this before, but I will say it again. We have our terminals here, right? I recommend always starting at the exact opposite end of wherever the terminals are. So we definitely could combine this. However, we see this guy, right? These are in parallel with each other. So to combine those two, do we need it to be in batteries or currents?
Currents.
Mhm. Exactly. So should we, in that case, keep this in current and combine these? Or transform those? Yeah. Okay,
Yes.
so let's go ahead and do that. 30 volts and 3K, that's an easier one, right? So we just got, what is that, 10 milliamps? Is it going to
Yes.
be pointing up or down?
Up.
Bingo. And then we have 6K, 3K, 2 milliamps down. So what will this combine down to?
Why don't we just use both functions? Why didn't we just use both voltage?
Because we cannot combine voltages in parallel. We can combine current sources in series and voltage sources, Lord. We could combine current sources in parallel and voltages in series. Can't combine it the other way.
Unless they're the same.
Hmm?
I mean, if both voltage sources are the same, then you could combine them in parallel.
They have to be the same.
Right.
But whenever there's resistors there, you can't do that because you don't know what the current's going to be through them. Yeah. So pretty much just keep it, if you have to combine things in parallel, make it into current sources. So now let's go ahead. What we see here, and I'll erase what I just, all of these guys. So now we combined this here now we see that there are 3 things in series, right? So do we want it in currents or voltages?
Voltages.
So let's go ahead and combine these, right? So what's that going to be? 66 volts. And you are free to do this on your test, kind of the way that I'm doing it. You don't need to draw it out every time. If you want to just kind of draw out bits and pieces of it. And then what's 3 in parallel with 6?
2K.
So I might go ahead and just. Y'all mind if I just erase this and draw it as the voltage? So 8 milliamps times 2K.
16 volts.
Is that going to be pointing up or down?
Up. Or positive up.
So now we can combine these in series, right? And I kind of went past this, but this current source is pointing this way. So that means that the positive end is going to be where it's pointing. That is the biggest thing that I see people mess up on. So we need to add these and make sure all of our polarities are correct. So what's that going to be?
16 volts with the positive terminal facing down.
What'd you say over there? 4,000. Oh, yeah, you're right. Okay. So now we're almost there, right? So we see current source in parallel, which means we gotta change it back one more time. So 4K, 16, what do we got? Pointing.
Oh, okay, sorry.
You're good. So let's look at this back from our circuit, and don't forget, I see so many people, that's the only thing whenever you're redrawing it. If you're not looking at the page, don't forget any elements. It's okay. So many people do that. We gotta remember this guy. So we have 4 milliamps pointing up. Huh. That's funky. Right? What happens when we add these two? So we have a 0 milliamp pointing down. Working. So let's look back at the thing. So it asked for current source in parallel with the resistance. So we are done. Now, the thing is, and this might happen, he might at the end ask for a voltage, which means if you get to the end and you have current, you have to combine it back to a voltage again. So don't forget that, but this is good. Now, for reference, what is a 0 amp current source?
Open
Open
circuit.
circuit. I drill it in, but it's so important. So what you could also do, you can either not draw it. I'd prefer if you don't draw the current source, just say like open or draw 0 amps. I'd prefer if you like say it's an open circuit. For me, it shows that you understand. So this is our final answer.
Probably resistor, but it's just not connected or anything.
Well, is the resistor still connected?
Oh.
So you got to draw the resistor. But you can say that it's no amps. So the combined, the equivalent is 4K. Now, what did we just do?
Reduce the network.
We did, but we just found.
Oh, the Norton equivalent.
We just found
Yeah.
the Norton equivalent. This is the other way. This is the kind of, if we, instead of turning everything off, we can always find the Norton's equivalent if there's no dependent sources by just reducing it down. There's a bunch of ways to find the Norton's equivalent. And Norton's equivalent is such a powerful tool. It's really, really cool whenever you're looking at like real life stuff. It is saying from two terminals, like to the rest of the circuit, to the rest of whatever you're doing, you know that there is a current coming out of it and that there is an internal resistance. That is so incredibly important whenever you're doing anything. Because you might not know what the actual circuit is, but you can always know what the current coming out is and the resistance from two terminals. And that's why Nortons and Thevenins are so important. And you'll get into that with circuits too, of like, you have just like a black box. You have a black box and it does not matter. It does not matter what that circuit is, as long as you know the voltage across the terminals or the current coming out of the terminal. So just some interesting stuff there. So okay, fair enough. Let's do the one that nobody wants to do. I don't want to do it either. So second order. Who thinks that they got it right on the test? And it's okay because a lot of people didn't.
think I
So
did.
the answer, nice. The answer on the test was a ridiculously high number of A2 was 5,900 and something.
Never mind.
Sorry. And A1, this is not the question from the test. A1 was like 1 million something. I was not expecting, I saw the answers on people's tests and I was like, there is no way. And sure enough, it was just ridiculously high number. I actually have a question. Do y'all want to do the one that was on your test or do y'all want to do this
Yes.
problem?
Both.
Solve them.
Probably.
Yeah.
You gave up.
Yeah, we
Okay, we can do that too. I'm so up for that. You know what? Where's my?
Go over this with you.
Okay, sweet. we can also. I'm going to, I have the solution is. Look at my test, but. I took a blank copy of the test and just wrote my name in giant letters across it. Would be for convenient if I could find that one. Oh, just. Because I have the solutions, I don't have the actual digital copy of the exam. So what I'm gonna do is I'm gonna write it. So I will say that it is likely that I would review the solutions for this one especially. And y'all do have the solutions and you have some questions on your homework where you have a variable in here. I don't know if y'all have gone over the solutions. But the fact that there is a variable there is important. That you have a variable in here.
Oh, the R7.
Mm-hmm. You might have to do that. Right, write that down.
Oh.
Hint, hint, wink, wink. Do that. Want to do this one? Okay, cool. I can also give the solutions for the other one. I don't know why Russell hasn't uploaded them yet. So, we'll go ahead and read this. Second order differential equation and initial conditions for the terminal voltage of a scaled RLC network with a current controlled voltage source, which that's what that means. CCVS is current controlled voltage source, but it's not entirely important right now, is given below, because he is not going to make you look at a circuit and develop the differential equations, because we cover a lot of stuff in this class and that's a pain. He's not all terrible. So he gives you everything you need. Fill out the table with the range of positive values for RM, where the conditions are overdamped, critically damped, and underdamped. And then we'll do. We're not even gonna do this. We're not gonna worry about that. We're gonna worry about the discriminant stuff. I would look at it, because that, I don't know if he's going to give second order stuff on the part one, because he hasn't covered second order in a minute. If he did, which I don't know this, so I can say this because I don't have insider information. It is possible that he might do the thing where it's like K1. It's like, it's negative T minus sigma, right? Negative T sigma. And then it's plus K to E to the negative T sigma. Look at that. That's on your chapter Z1. Let me make sure I'm not doing this wrong. I have way too many. This is so incredibly random and not important, but everybody hates on Edge, which I also hate on Edge, but Edge cracked the code for PDFs. Edge is totally optimized for PDFs. I have like 20 PDFs open at any given time. And it's pretty okay with me. It doesn't hate me. Totally random. But look at this, the like Sigma thing. I would know that, but don't stress over it too much. Just kind of thing. So. Whenever we are looking at conditions, what should we think of? Discriminant, not determinant. It's not called determinant. Called discriminant. I didn't count off on anybody's papers if they wrote discriminant and if they wrote determinant and wrote the correct equation for discriminant. It did crack me up a little bit. But just for reference, it is discriminant. It's disc. D-I-S-C, discriminant, what is the discriminant?
Everything under the radical.
Exactly. We are looking at that quadratic formula, which y'all have not looked at since probably high school. And we're looking at this radical thing. It's radical. I am
It's like Adventure
a
Time.
dork. Yes. Yes. I am secretly like a 45-year-old man. So over here, what is b squared? That's the easier one, right? It's the middle one. It's the second one. Yes, I think don't have to. I like the solutions for the midterm you did. It should work out the same. I, by and large, probably would.
Are you talking
But-
about normalizing?
Yeah,
Okay.
normalizing. But for this one, we're not going to. Or just because it makes it a lot simpler. So, and I say that because Russell didn't, so it should work. That's not like my favorite answer for something, but we're gonna go with it. So this is our B. Is A the first one or the second one? Third one? A, B, C. However, yeah. So we have, what is our B squared? It's 6 minus 2RM squared, which is going to be gross, minus 4 times A, which is 5. Um, 5 minus RM times C, which is 2 minus RM. Yeah, y'all are gonna have to tell me what that equals. I guess I could do it. Right?
I didn't multiply the form, but I got R squared minus 7RM plus 2.
So we can do that. Let's go ahead and simplify that out. So we're gonna see, make sure that you do that minus. We're just gonna go ahead and do that. Minus minus 4 RM squared plus 21, no, 28, right? Times 7, it's 28.
Yep.
Okay. So 4 RM squared minus 4 RM squared. 0. Yay. There's not an RM squared that we have to deal with. 12 RM, negative 12 RM plus 28 is
16 RM
16. And
minus 4.
I got 24 RM on that first one instead of 12.
yes, it should be 24.
See,
You're good.
Oops.
Thank you. Thank you. 24, which makes this 4, right? 4 RM.
that's
Or-
what I
Cleaner.
Yes. 4 RM minus 4. So now let's look at the range of RM. So we see that it's positive values. So no matter what, it's going to start at 0. So what is, let's start with critically damped because that's what you had to do on your test. When it is critically damped, what does that mean?
RM is equal to 1.
It's equal to 0.
Or
It's equal to 0.
which would make RM 1.
Critically damped. Oh, yeah. You're good. So we're going to set this equal to 0 for critically damped. Which means that RM is equal to 1. So these are all ranges, but for this one, there's only one value. So now overdamped. What is overdamped condition?
When the discriminant is greater than 0.
Mm-hmm. So what's that going to mean?
Can be greater than 1.
Mm-hmm. So it's going to be RM is greater than 1, which makes the last one a lot easier, right? There's only one other option if it's less than 0, right?
So then it's less than 2.
So it can be and make sure you don't make this. So we see that because RM is equal to 1, this sign cannot be less than or equal to. It has to be less than because, yeah. So not too bad, right? Not too bad. Okay. So he makes it so they aren't too scary.
The thing point variable. And
Yes.
string.
Yes. So make sure you know how to do a variable.
now those like where you say overdamped, critically damped, and underdamped are equal to 0, less than, or greater than. That's in Z1, right?
Yes.
Okay, because that would be something I would forget.
Yes. It is in chapter Z1. Here, I will grab.
Yeah.
Yes. And I am actually kind of blanking on the condition for undamped. It's
Thought it's what you wrote, 0 less than equal to RM less than 1.
no, so that is underdamped. So there's a difference between underdamped and undamped.
Oh.
So So I'm gonna grab a table really quick. So, I have it, don't worry. Sorry, guys. I got this one. So, table. My computer about to die, yes. So overdamped, this is P1. And I hate this. I hate how this is formatted. But what this means here is that that square root is going to have imaginary conjugates. What does that mean? Mm-hmm.
There's going to be negatives under there.
Mm-hmm.
But you have to use I.
Mm-hmm. And that's whenever you get to like this part, like generating the time domain expression, that's when the negative stuff gets really gross, because that's when you have to start doing sine, like when you have to do the cosine thing. Yeah. But we're not gonna worry about that. Right. I'm gonna make sure I'm telling y'all everything. Just wanna be very sure. Yeah. Yeah. But oscillatory is that undamped one.
This one's on our homework too, isn't it?
Yes. Yes. Should be. Yeah.
Yeah, because the one from our homework ain't up there, table, unless if this is table.
No. That table is directly from chapter Z1. I have Z1 pulled it up. Yeah. So I just grabbed Z1. And then the undamped or oscillatory case is on page 16 of Z1, if you want to check that out. The undamped or oscillatory. They're the same thing. Undamped and oscillatory mean the same thing. And the reason that that's not on the table is because, or the reason that's not asked for on this problem is because it's not oscillatory. That's kind of what that means and why.
And the only way we know that we're working with discriminants is if we're given initial conditions. Or conditions.
So you can work with discriminant with just this first guy here.
I think
If
the initial
you-
conditions are given for the time domain expression, right?
Yes. So if you have time domain expression, that's when you need the initial conditions. Because that's when you're going to make that K or you're going to work with cosines or that K equation that I said, which is all in Z1, but don't worry about that.
This case.
Remember this, remember how to find the discriminant.
You said like this how.
Yes.
Yeah.
That's what that RM is. Okay. Okay. Grabbing my Russell cheat sheet. Okay, Norton's. We're gonna do Norton's one more time. Because I think this is it's a good problem. It's not too bad. And I really don't want to make today insanely long for everybody's sake. I have 2 presentations on Tuesday and I'm kind of stressed about it. Speaking of, we need to work on that.
Oh, I totally forgot.
Yeah, me and Abe are in a group together for one of our presentations. They were giving him like, so you realized you're in the group with your TA. It's fun. We're having a good time. Okay, so Norton's. Russell gives on this question, I'll read it. The resistive network contains a voltage-controlled voltage source and a voltage-controlled current source and is driven by a 22-volt DC voltage source. Calculate the values for the Norton's equivalent, which is shown down here, and express Jn and Gn in numerical form for maximum speed and efficiency. Apply the MAME to this problem. So, apply the MAME to this problem. And really, I have not seen, like, the people who try to do KVL and KCL or other ways to do it, whenever there is a dependent source, it really makes it hard. It really does. And he's going to give you a dependent source. And so it's not too bad. Let's do it together. So whenever we think Norton's, we're going to think MAME. Norton's equals MAME. MAME. Voltage or current sources?
Current sources.
No,
No, voltage sources. Shit.
voltage sources. Mm-hmm. We're going to do mesh currents. And then name is the exact opposite. I always would write this on my cheat sheet. Just this little thing of what I should be looking for. Because this is what tells you what you should transform your sources to in the circuit. Because we see here that we have a current source, but we want voltage sources. So we're going to need to transform that. And then, is it weird to y'all that we're trying to find Norton's, which is a current source, but we need voltage sources?
No, because we're solving for the mesh currents.
Exactly. You're solving for mesh currents. You're solving for what's going to end up being the current through this wire. And that's going to be what your current source is for Norton's. So that's a little bit of an explanation there. But so first let's go ahead and pen. transform that, right? And then there's one other thing that we're going to do for Norton's or Thevenin's. And it has to do with these two terminals. What are we going to do between these two terminals?
Short them. Or no, inject a 1 amp current source.
Yeah. So it's for specifically this, we think voltage sources. So we're going to inject a voltage source. And we call it E. We call it E naught. Yeah. And it's okay. As long as you write a voltage source, I'm not going to. Yes. Because I find it pretty interesting. Number one, because we need voltage sources for our mesh. But two, we use a voltage source for the properties of it. To find the current through it, what is a 0 volt voltage source? So what we end up doing is we just find the current through that wire, through the 0 volt voltage source. And then whenever we set eventually E naught equal to 1, we know that V is equal to IR, and we're going to solve for G. So we know that we have current. But we want conductance. So R equal to V over I. But we don't want that. And this got some people. We want G. G is equal to 1 over R, right? So can we say that G is equal to I over V? So we're going to end up having this V is equal to 1. And then whatever we get for our mesh current, it's just that over 1. So whatever is in that matrix is actually what's that G value. You don't have to do 1 over it. Cool. And that also, at some point, maybe write that down. So we add our E naught. That's why we add a voltage source. Does that make sense? What part of it doesn't make sense? So we need conductance, right? We're going to utilize Ohm's law. Yes. You are completely right. And that's why it's kind of counterintuitive. We keep all of the values in the matrix resistances. But then at the end, we know that we're solving for current. If we want conductance, we can just divide that current by whatever we set E naught to, which we're setting E naught equal to 1. Which means that our mesh current at the end, we divide that by 1, and now we have conductance, according to Ohm's law. Sorta, kinda? Okay, well, I hope it makes more sense when we plug numbers in. So let's go ahead, let's transform our current source and write out our matrix. So what is this voltage source gonna end up being? We're gonna have our 1 kilo ohm resistance.
GM V1 R3.
Mm-hmm. And it's pointing this way, right? Because we have our plus, minus, pointing towards the positive. It's pointing towards the way that current's gonna flow. And so, do you want me to redraw the circuit again? Okay. I can do that. Oh, I should totally not make that a battery. It's fine if you make it a battery, but technically it should be this diamond guy because it's dependent. A battery means it's independent because it's a battery. A battery isn't going to have dependent stuff in it. Okay, 500. Okay. So now we're going to see that. That's gross. So we need our equations now. So this is where our V1 is. And then from here to here, it's our V2, which is nasty. It's nasty. So how are we gonna write that equation? We got thoughts?
Will we start with the resistance portion of it first? And I guess we'll have like two meshes. Draw the arrow for the current flow.
Mm-hmm. Yeah. So it does work the other way if you keep everything else the same, but we in this class always go clockwise. Did I just move everything? Of course I did. It's fine.
We need to change all the resistances to Siemens, or is that with Evans?
That's Thevenin's. That's name. And that's the other thing that we should think of that I forgot to write down. MAME equal to resistances. So now let's go ahead and write out our passive matrix first. The easy one. Going to be a 2x2 because we have 2 loops. So what are all of the resistances in loop 1? What about shared between 1 and 2? Negative 2k. And then all of them in the second mesh. Exactly. It's going to be our IM1, IM2 is equal to So now let's go ahead and just write all of our sources. So for loop 1, I have this guy. Is that going to be plus or minus 22? Then what about this guy? Next guy. Yep, that's mu. That's just a bad mu. Okay, and now let's look at the other guy. So first up here. Ah. Oh, please don't die. Sorry about that. Computer almost died. Okay, so we got positive, right? GM V1R3. Hang on, my pen is not working. It's been a technology. It's been a great day. It really has. It has truly been a fantastic day. Hold please while I wrestle dramatically with technology. Okay. Now are we? Oh, look at that. And we're back. Hypothetically. Are we back? It was back, and then I went back into tablet mode, and now it's angry again. Oh, come on. You're so close. You want to respond so bad. Do you want me to just not be in tablet mode? Is that what you want? Gosh. Oh.
You're muted. Can y'all hear her?
No.
Okay. Can she hear us is the question.
I don't think so.
Oh, that's clever. There you go.
Okay, I'm back.
Yes.
Sweet. Oh my gosh.
Just banging it against the desk or something. It always works for me. Violence is the answer today.
It is the answer. It's hold on. Let me reshare because I can't actually tell my computer to go to OneNote by itself. Okay, we're back. So separated out those things. Y'all saw me do that. It's going to be funky how we write V1. And so here's how we're going to do it. We see that this positive is here, right? I'm going to write it as this node is the positive side. And then the negative side is at ground. Is it the same voltage going over that 2K and that mu V2 as it is going this way? Are those the same voltages? I think that it's a lot more easy. It's a lot easier to not have dependent variables in the equation for the dependent source. So we're going to do that. So we're going to go ahead and write out the equation for V1. So to get that, we need the voltage drop over this resistor first, right? Okay, hold on. Gonna backtrack. So to find the voltage this direction, we need the voltage drop over the 1K and the 22. And that's the same as the other way around. And I can rewrite this to kind of make it a little bit more sense. Make it a little more obvious that they're the same. So what I just did, I didn't change anything. I just kind of moved it down. And now we're going to say that this is the positive and this is the negative. Does that make is it a little clearer now? Okay. So, I don't like this one here. So what we're going to say is we're going to find the voltage from here to here, and then we're going to find the voltage from there to there. And this is, we're finding the parameter, which means that voltage drop is positive. So we are looking for the positive voltage drops. We're not looking for the voltage rises right now. And remember, our current is going this way. So what is the drop from this positive, from positive to negative here, in terms of IM1? For the 1K. Is it positive or negative? It's negative because there's always going to be a voltage drop over a resistor in reference to the current. The current is flowing this way, which means that the current is saying that the voltage is the exact opposite of what we need. So that's why, in reference to the current, the voltage drop from here to here is negative IM1, 1K. Sort of, kind of. I know that that's like, it's a little rough.
It's not working.
You're not doing it hard enough.
I think you're right. I am not clicking hard enough. Okay, we're restarting my computer. We're restarting.
A little bit of, possibility.
Yep. audio is on. I'm unmuted. Let's get back to it. It should be working now. Should have saved. Lovely, it did. That makes me very happy. Okay. We can write. Beautiful. Lovely. So V1 is going to be equal to negative 1k times IM1 plus 22 volts. Does it make sense why it's plus and not minus? It is a voltage drop this time. So now we're going to do V2. So we're going to do the exact same thing, except instead of an independent source, we have E naught. Yes. Yes, it is. It is, but then it does a weird thing. We're trying to write them in terms of mesh currents, right? Because we want to separate out the variables. Because, and I say this, I repeat myself a lot because try to make sure the concepts get nailed in, but what this is a constant R times basically X. Your IMs are your variables in algebra. And what we're trying to do is get all of the variables over to the left side, just like we did back in 9th grade. And so we want to write these gross things in terms of X, so that we can get all of the X's over to the other side and all of our nice pretty numbers on the other side. So that's why we don't want to write it, because then we would have to do a system of equations where we would write V1 in terms of V2 and V2 in terms of V1 and solve them. Or we could go the other direction that has numbers. So I'd pick that way. So exact same thing. We're going to find plus to minus. So let's do plus minus, right? So what's that going to be? It's going to be 500 times positive or negative IM2. It's going to be positive this time, because if we look at the direction of our current, we're flowing clockwise. And that's in the same direction as this positive and negative that we're saying. Does that make sense? You're still confusing. Still confusing?
A little.
I'll redraw it. I'll redraw it so it looks the same as the other one. Yes. So we see that positive side is up here. So this whole thing is the positive side. And then this whole thing is the negative side. So we, over this resistor, want this positive, negative, and positive, negative. So let's look at this current, right? So current is going to be flowing this way, right? So according to our current, the voltage drop is going to be this way. So now is that the same or the opposite of what we are trying to find from that plus and minus? Same. Okay, so that's why it's positive. Does that make a little more sense? Okay, sweet. So it's going to be 500 IM2 plus or minus, plus or minus, plus E naught. Because once again, it is the same direction. The positive and negative terminal are the same direction as the current. So now what we're going to do is we're going to take this and we're going to plug it in down here. So we're going to do mu times 500 IM2 plus E naught. And then down here, we're going to do GM R3. I just pulled out R3 because it's a constant, times I lied, that's minus. Did y'all want to write the mu and the GM and the R3, or do we like it stayed as constants? Or as letters? Letters, okay. So this is a little weird, right? We've never had, at least I don't think we've had for y'all's problems, independent things in the dependent matrix, right? All that we do now is just separate it again. It's not terribly, we're just gonna take, let's do a highlighter. We're gonna take these things and just pull them out. So we can do another intermediate step of, yes. I should give it back to you on Monday. I appreciate you so much. Thank you. This isn't even my pen. I had to borrow a pen because it was all supposed to be on documents and paper. But we're gonna pull it out. So let's write out our matrices again. Let's write the independent one. Do we have any extra independent things on the first row? No. What about on the second one? Right, we have that 22. So we have to figure out what GM, oh, it's all the way back over here. GM is 2 millisiemens times R3, which is 1K. What does that equal? Just 2? Sweet. GM is equal to 2, mu is equal to 4. We're gonna write that over here. So that means it's 2 times 22, right? You're good. So then we're going to have our dependent, and then plus, right? Let's pull out our E naughts. So up here is going to be 4 E naught, right? 4 E naught. And then down here we have our negative E naught and then minus 4 E naught, which is negative 3 E naught. Yes, negative 5 E naught. So kind of funky, but we're going to treat it the exact same as we always do. So now we can rewrite our dependent matrix. I'm just going to go ahead and write it again, and then we'll separate it out into a matrix. We're going to write everything out this time. Do you mind if I go ahead and write in the 4 and the 2's? Can we do that? We're going to do that. So 4 times 500 is equal to 2,000 IM2. And then we have negative 2,000 IM1 minus 2,000 IM2. Right? So let's go down again. We're going to separate it out into a 2 by 2 matrix times IM1, IM2. So we have 0, IM1, 2K, negative 2K, and negative 2K. Slow me down if I'm going too fast right now, but I think we've done MAME and NAME a lot. Okay. Now we're going to do what we always do. We're going to draw a big old arrow, and we're going to subtract. So let's write out our matrix, our matrix of 3K minus 0, 3K, negative 2K minus 2K, negative 4K, negative 2K minus negative 2K, 0, 3.5K minus negative 2K. 0.5K. Now, what is that equal to? Right? What was that? 4 E naught, negative 5 E naught. So we're still going to solve it the same way. However, the only difference is this time we're going to have numbers other than 1 in our E naught matrix. Otherwise, it is the exact same. And remember that to find J Nortons, we set E naught equal to big ol' 0. Then to find G Nortons, we're going to set E independent equal to 0 and not equal to 1. And then we put it in our calculators. My joints pop a lot. My bones are messed up. And then for our JN, we are we going to use IM1 or IM2 for our JN? We're going to use IM2 because we want the current flowing through from A to B. So that current is IM2. And it's the exact same thing over on GN. Let me know what y'all get.
I got 8 milliamps.
That's a nice, good number. 8 milliamps, everybody agrees. And then what about our GN? And remember, when you set E naught equal to 1, you're essentially setting it equal to 4 and then -5. Remember. If that wasn't clear. -9. Is it milliamps? Oh, Siemens. Mm-hmm. Is it exactly 9 or is it 9 and some change? 9.99. Cool. Well, so give me like a couple.
I don't know if I get more.
That's-
I don't know if I make it more.
Oh, you just got 9. Did you make sure to do 2K? It probably should be milli. Because it's like 3,000, 4,000. You're good. You're good. But good number of steps, but solve the problem, right? Anybody have any questions about that one? Does it make sense, or do you want me to go over again why we just use that second mesh for GN? All right. So technically, they are right. It is 9.09 milliamps. However, it is flowing through a 1 volt battery. We are trying to find, oh, that's right, I moved that and it erased it. We are trying to find the current through this, or we're trying to find the equivalent conductance from A and B. So we say that we have the current flowing, we have the voltage. So if we use our Ohm's law of G is equal to I over V, we set E naught equal to 1. It's 1 volt battery. We say our IM2 is over, which is 1. So now it's just our IM2. It's IM2 divided by 1. That's why it's 9 millisiemens. Sweet. I dig it. So where are we at, everybody? Tired, hungry. I know. I know my reviews go on too long. I talk too much. Do we want to go over more stuff, or are we ready for lunch?
I was gonna ask you, so like earlier you said it doesn't matter which way you organize the ENOT source, as long as you insert the negative in the matrix. What do you mean insert the matrix?
So, over here, I wrote negative ENOT. Because in the loop, it's a negative voltage rise. It's exactly how you would do your normal sources.
Because it's going in the opposite direction of the current. From the, okay.
You're good. Yeah.
No, yeah, because the way that I did this problem was I flipped the ENOT.
Mhm.
I didn't place negative because my thought process was, okay, so since I have it upside down, it's moving relative to the current of the mesh loop.
Exactly.
Okay.
Yeah, that's right. If you might, however, at the end get negative.
Which I did.
And so you have to divide by -1 that time. Because look, and this is kind of why I write it positive. RJN, we define it as flowing up. And so I write my ENOT as flowing up because that's in the same direction as our J0. Kind of weird.
Oh, so whatever the current source is pointing as a result, you should organize your ENOT some direction.
And it'll usually be up, but then it ends up just being negative in the matrix. Funky.
And so like anytime you get anything that's negative, you just divide by -1. Or
In this very particular circumstance of Thevenins and Nortons, if you normally get negative, you should not just divide by -1. However, if you flip your source on these types of problems, you just have to figure out if you're supposed to divide by -1. Typically, if it's negative, you just have to divide by -1 and you just flipped your source. Work it out,
Yeah.
see how, yeah.
In a different order, the example, they didn't separate these two until they got collected. Do that.
It's preference. Is that what Russell did?
I think I wanted to.
Yeah. Yeah, it's either or. I like separating it out early. Other people like separating it out at the end. As long as I can follow your thought process, or if it's right at the end, I don't care.
Do you have a good example for quick division? That would, like, you don't have to solve all those things. Did you have any quick division?
No, that was the one I didn't have. Although honestly, if you want, that's one of the ones where you can look it up online. Current division is current division. And the big thing we can just do really quick over here, current division. So if it is only 2 branches, and only if it is only 2 branches, the current through a branch X, and here, hold on. This is our I total. We're going to say this is Rx, and this is Ry. So the current through Rx, so Ix, is equal to I total times ry over rx plus ry. So on the top is the opposite one, and on the bottom, it is not the parallel combination, but instead the just two values added together. And I'll see people that get people too.
You use the opposite resistor, like, for example, you're trying to find the current that goes through RFX, you use RF1.
Yes, so this gives this current.
Yeah.
And this is because current, well, voltage is directly proportional. The more resistance, the more voltage drop. More intuitive, yeah.
So the resistors in series.
Hmm?
The resistors are in series with people.
No, these are in parallel. Because the current through two resistors in series is always going to be the same. And the voltage drops across two resistors in parallel is always the same. Also, if it says to use current division, please do not find the voltages and find the currents that way. If it's, I know that might be easier, but if it says to use current division, please use current division. Yes. However, you have to give me the right formula for current division. Cool. Cool. And then, however, if you have more than one, so if you have RZ, this no longer works. Instead, you have to, stop it. Exactly. So in this circumstance, and if you want, you can always do this. This works whether it's two or all of them. You do 1 over Rx divided by 1 over Rx plus 1 over Ry plus 1 over Rz dot dot dot. So on this one, you want on top, you want the one that you want. You want the current through the resistor that you want over 1 over all of them. However, it is not them in parallel. You do not do 1 over them to the -1. You do just the combination of all of them inverse. The inverse of all of them added. So if they were 2, 3, and 4, it would literally just be 1 over 2 plus 1 over 3 plus 1 over 4. That would be 1 over 2. So it would just be that, which is something. Cool? Okay, sweet. I say we break. Okay, sounds good. Perfect. Do we have any questions here or online? Good stuff. I will see you on Tuesday, bright and early at 8. Remember, it is at 8 a.m., not 9:30.
Tuesday.
Thursday. I said Thursday.
You said it's Tuesday.
Thursday.
You just scared the hell out of me.
I am so sorry. Thursday, May 2nd. I will see you. Except I will see you on May 2nd.
Wait, so the
On-
one over 2 is on Thursday, 8 a.m.?
Yes.
8 a.m.?
Yes. And if you want to check that, it is on the UTA website on your final exam schedule. Also,
also on the syllabus?
huh?
Is it also on the syllabus?
Yeah.
Probably.
On the syllabus, it says 11.
Yeah. It's supposed to be 8.
It's whatever UTA website says.
Okay. I will be here at 8.
Yeah, for real.
And then one more thing, actually, before you all head out. Russell teaches electronics over the summer, and I highly recommend doing it if you can. If you have an internship, if you have anything else, I understand. It's at 8 a.m. over the summer. It's rough, but it's a lot more fun. Russell has a better time teaching it over the summer. You're able to be more involved and really enjoy it because it's a fun class. And there's going to be some really good students over there in it.
I think you mentioned in class that it was 4.
It's not full.
Oh, it's-
It'll like, he was worried, it doesn't make sometimes, like it doesn't have enough students in it. But it'll be good, and if you can, I recommend doing it. Yeah, he teaches in the fall. Luckily, he doesn't teach in the spring.
Electronics?
Yeah,
Okay.
Alavi teaches it,
Yeah.
so I do not recommend doing that. No, electronics 1, there is not.
Is there terms to-
Yes,
oh,
there is electronics 2 class, and there's a lab for that. But yeah,
What's the course number?
2303. 2302 is passive and active. But yeah, I recommend doing it if you can. It's a good time. No, it's full. It's the full semester.
For this on?
It's a full summer. I forgot what the actual number of weeks is.
I'll memorize.
But yeah, okay. Y'all have a good one. I will stop recording as well and end this. Au revoir. You as well. Bye.